Okay, then, and this is the last part of graphs. This is the end of chapter 8, planar graphs. So in this lecture, we'll define what a planar graph is. I was supposed to have deleted planarity is. We'll define what a planar graph is, what a complete graph is, and how to tell if a graph is planar. And so as we said, graphs can be drawn in a lot of different ways, and some of them involve crossings that are not vertices, right? Like these two, we know these are the same graph, just drawn different ways. This highlights the fact that it's bipartite. This highlights the fact that you can draw it without any crossings. But some graphs always have crossings. You cannot get away from drawing it without crossings because you're drawing in 2 dimensions, and 2 dimensions is a tricky place to draw things. And these graphs are called non-planar graphs. So planar graph, this one's planar. Because it can be drawn without, not without graphs, without crossings. Okay. Why is planarity important? If you're designing a chip, a microchip, something, essentially what you're doing is you're spraying a circuit onto a substrate, and the circuit is 2-dimensional, right? And you don't want the wires in your circuit crossing because that short circuits out it's a short circuit, it'll destroy the chip. So when you're designing a chip, you have to make sure that your designs for your chip is a planar graph, right? And then you can go in and then you can actually build them. So if you Google chip design, right, you'll see a lot of different things. So when you're trying to wire something together, you got to make sure that the wires don't cross because you're just spraying metal onto a substrate. If this was a chip, right, you might have come up with this design and then you said, okay, well, we can do it like this. It's the same thing. So to talk a little bit about what makes something planar or not planar, we have to talk about complete graphs. And a graph is called complete if every vertex is connected to every other vertex. And a complete vertex with n vertices is symbol kn. So this is k1, one vertex, no edges. K2, both the vertices are connected to it. K3, each vertex is connected to both of the other 2. K4, each vertex is connected to all the other 3. And note that each vertex is degree n-1. In K4, there's 4 vertices. Each vertex is connected to all the other vertices, so that means there must be 3 edges coming out of it. And you can draw what the next few graphs would look like. K5 would be 1, 2, 3, 4, 5 vertices. You'd have to connect each vertex to all the others, and you get that, and that's K5. A bipartite graph, it can be called complete if every vertex in one group is connected to every vertex in the other group. And these are symbols K and M. So this is K22. Each vertex here in this group is connected to every vertex in the other group. This is K24. These 2 are connected to every single one in the other group. Each of these is connected to every single one in the other group. So those are complete graphs of bipartite complete graphs. So when drawing complete graphs, you usually have crossings, right? If you can try and draw a complete graph like this or like this, you generally have crossings. The question is, can you get rid of the crossings? And the answer is you can for some of them, but these 2 you cannot. Right? K5, no matter how you try to draw that, you're always going to have to draw it with some crossings of edges that aren't at vertex. Same thing with K33, right? There's no way to redraw that without some edges. So play with those a little bit and see if you can redraw them without crossings. You won't be able to, but by playing with it, you get a feel for what's going on. And so Kuratowski, the 1900s mathematician, has a theorem. If a graph can be reduced to either K5 or K33, then it is not planar. So if you can reduce a graph to either one of these two, then you can't get rid of the crossings. And reducing a graph is a game. You start with a graph, you can do two things. You can erase an edge, and you can relate, whenever you have a degree 2 vertex, you can replace it together with its two incident edges. You can replace that by an edge. And if you start with one graph and you reduce it, you get a graph H. They're called homeomorphic, and you'll see that term in the text. So if by playing this game you can get to either K5 or K33, your graph is not planar. You can, of course, delete all the edges and get a graph that has no crossings, but that doesn't actually help, right? This is a game to show whether or not one of these two graphs is a reduction of the graph that you started with. And if one of these two graphs is a reduction of the graph you started with, then the graph you started with cannot be redrawn without a crossing. So just as a little note about K33, about what the problem is. So K33 is 6 vertices, and they need to connect everything in the top row to everything in the bottom row and vice versa. So if I start connecting things, I can connect this to this, this to this, and this to this. So that's okay. And then if I try to connect this to these three, well, I can do this directly, but I can't just go straight down here. And I can't go across here because I don't want any crossings. So I could draw this like this, and I could draw this like this. Right? And so we have almost everything connected. But I want to point out a feature here, and this is, I'll make all my vertices bigger so we can be clear about where they are. About why non-planarity happens is that now I have a cycle. Let's see, what's my cycle? I have a cycle. This is the cycle that I want. Here, 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 and there. So I've got a cycle. These two vertices I want to connect, but this one is inside of the cycle and this one is outside of the cycle. There's no way for me to draw a line that connects this to that without going through, right, without crossing the cycle at some point. Right? And so that's sort of the problem with planarity is, does your graph, no matter how you draw it, always end up with a cycle where one vertex is inside and one vertex is outside, and you really need to connect those two vertices. So here's a graph. This one is got a bunch of crossings, one here, one there, one there, one there. Is this planar or not? It is actually planar because we can just redraw it as a different graph. So I will put in A, B, C. So if we look at this cycle, right, that's sort of the boundary of it. And the problem is that D is inside the cycle, so there's all these crossings. But if we take A, B, C, E down here, F down here, and G down here, my cycle looks like that. G is connected to E inside, that's okay. And A is connected to E inside, and that's okay, right? But let's take D and put D out here. Now, where is D connected to? D is connected to C, D is connected to E, D is connected to B, but I can go around like this to get to B. D is connected to F and G, but I can do that and that. So now I've got two drawings, two isomorphic drawings of the same graph, but I can redraw it without any crossings, and so that means it's a planar graph if you can move points around. So here's a graph, example 2. This is a graph that is not planar, and we want to show that it is planar. No, this is a graph, we don't know whether it's planar or not, but we want to show that it's not planar. We want to play this game. I'll call it the reduction game. The rules, you can delete an edge. And if you have anything that looks like this, which is a degree 2 vertex, you can condense it into just a path from A to C. That's an arrow. So those are my two rules. And if I end up with either K55 or K33, then it's not planar. This only has one crossing. And the question is can you ever get rid of that crossing by redrawing it? So let's think about K5 for a moment. K5 has 5 vertices of degree 4, because K5 is, K5. I had a picture of K5 somewhere. There's K5. So 5 vertices of degree 4. If this is going to be planar, not planar, I better have, all I can do is I can delete edges. I can't delete vertices. And I can do this kind of series reduction. This was what it's called. So what I can't do is I can't increase the number of edges that go into a vertex. I can't increase the degree. So if I want 5 vertices of degree 4, I better make sure I have at least 5 vertices of degree 4 here. A is degree 4, C is degree 4, D is degree 4, F is degree 4, E is degree 4, H is 1, 2, 3, 4, 5. C is also degree 5, isn't it? So I've got plenty of vertices of degree 4, so I can try to construct. So my goal would be to try to construct this is going to be a terrible drawing. That graph from this graph using these rules. So what I'm going to do is I need to redraw it so that I get a nice set of 5. So I'm going to pick A, C, F, H, and D, right? A, C, C, F, F, D, F, D, D, A to C, C to F, F to H, H to D, D back to A. That's a 5 cycle. And I can take that as sort of my outside cycle. So what I need to do then is think about where my other vertices are. I've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. I have to locate the other ones. We'll put B out here. We'll put E down here. And we'll put G down here. And G is a little bit off the top. And so we want to actually get rid of B, E, and G if we can and redraw this so that it's actually looking like that. So let's redraw our graph. A is connected to B. A is connected to C. A is connected to D. And A is connected to G. Right, so there's all the connections for A. It's a degree 4, and we got all those. B is degree 3. It's connected to A. We've got that. It's connected to C. And B is connected to E. And so there's all the connections from B. We'll just go through and fill in all the rest of the connections. C is connected to A and B. We've got those. C is connected to D, which is across. C is connected to H, which is down here. And C is connected to F, which is down there. So there's the connections for C. What about the connections for D? D is connected to A. We've got that. D is connected to C. We've got that. But D is also connected to F and H. D is connected to F and H. And you can see the beginning of K5 sort of in here. E is connected to B. We got that. E is connected to F. That's this. E is connected to H. That's that. And E is connected to 1, 2, 3, 4. There must be another one. 1, 2, 3, 4. E is connected to G. Okay. So there's a graph with all the connections from E. The connections from F. F is connected to C and D. We've done that. F is connected to E. We've done that. That's one of the benefits of doing this stuff in alphabetical order. I don't need to draw the connection from F to E, because I've already drawn the connection from E to F. F is connected to H. That's that one. A, B, C, D, F, G. Well, we've got the connection to A. We've got the connection to E. We just need the connection to H for G. And then H, 1, 2, 3, 4, 5. So H should be 1, 2, 3, 4, 5. Great. So we've redrawn the graph. We have a crossing in here. We've moved this crossing from there to there, but that's okay. Great. So we almost have what we want. We're missing, we've got the outside. We're missing this, and I'm missing this, right? Those are the two things that I need to get K5. So how can I do that? Well, I need a connection from A to H, but if I delete this, that means now G is AGH. This is a degree 2 vertex. A degree 2 vertex, I can delete the vertex and end up with a line connecting the outside vertices. So I can take this path, AGH, since G is the middle degree 2 vertex, and I can just replace that oh, where would pen go? There it is. With this one. And similarly, we need A connected to F. Well, we can go from, that'll be A to B to E to F. That's one way to do it. How can I get that? Well, if I delete this, then I can replace A to B with, I can replace ABE with just a path directly from A to E. But if I have a path, if I delete this, then that means once this is deleted and this is deleted, I can replace this with a direct path from A to E, but then E is a degree 2 vertex, so I can replace the path that's AEF with just that. So we ended up with A5, K5. So it's non-planar. What that means is if you want to redraw that graph without any crossings, you won't be able to. And try it out if you're interested. I think you can. Okay, so that's graph theory. We'll start up, the next section will be on trees.